Hi, my name is Zachary Lyons, and today I'll be presenting Physics 2212 at Georgia Tech Lab number 3, the magnetic field of a bar magnet lab. In this lab, the goals are to find the distance dependence of a magnetic field of a small bar magnet. We're going to measure the magnetic field on and off axis using the Biot-Savart law. We're going to simulate the magnetic field using Python, and we're going to compare our experimental data to our computational model. The findings of this lab is that the magnetic field magnitude increases as distance decreases. The magnetic dipole moment is roughly 7.91, and the measured off-axis field was approximately 1.4 times 10 to the negative 4 Teslas. The simulated off-axis field was 1.567 times 10 to the negative 4 Tesla. Some key concepts for this lab is the Biot-Savart law. This relates the magnitude of the magnetic field in Teslas with the distance away from the source to the observation point and the current running through an object. The magnetic field dB for a small section of an infinitesimally small dl is shown here to the right. And for a loop and a dipole, we can find the relationships here. It's for a distance that's much greater than the radius of the loop. And the magnetic dipole moment is equivalent to this equation here. And it's the same direction as the conventional current, which we can use in our model computationally. Some key concepts continued. The magnitude of the magnetic field of a magnetic dipole on the perpendicular axis is half that of the on-axis, and it's given by this equation here. The direction of the perpendicular axis is opposite to the magnetic dipole moment, and the magnetic field magnitude due to a bar magnet is shown by this equation here, which can help us solve for K, which is a combination of constants. This we can find experimentally, which is how we calculated for the dipole moment experimentally. This is a visual model. The system is the magnetometer in our phone that we use to calculate the magnetic field as experimentally. The surroundings is the bar magnet, which is the source of our magnetic field, and we treat the bar magnet as a magnetic dipole. So here's our procedure. Our materials are a bar magnet, meter stick, tape, and a magnetometer, which we used in our phone. We had to compensate for magnetic north and orient the phone such that the app has read an X component of 0 for the magnetic field. We had to find the magnetometer chip and then measure on-axis magnetic field. So as we move the phone farther and farther away, or closer and closer to the bar magnet, we can see that the magnetic field was increasing. We had to take 3 measurements per field. And then we had to measure the off-axis field. So we measured a distance away 45 degrees from the dipole, and then we measured the magnetic field at this distance, and we repeated it 2 times. Here is our experimental data for the lab. As we can see here, as the magnetic field gets greater, our distance away gets closer. And here is our line of regression for the magnitude of the X component of the B field as distance increases. So our data here was represented. The equation of the regression line is shown and given by this equation, and the slope of that equation gives us our n and y-intercept L and K. So we could solve for K using this equation here. And we had to correct the magnetic field component in the y direction because of Earth's magnetic field. So our observations were that when the magnetometer is far away from the magnet, it measured a near 0 magnetic field in the X direction. And as the magnetometer got closer, the X component of the magnetic field increased. Here's our computational model with our constants. Here's us setting up to solve for the magnetic dipole moment inside of the code. And the code to the glow script is shown below. Here is the code that sets up the perpendicular axes and all the arrows for the code. And this also gives our vector for the 45-degree magnetic field. And here is our results. As we can see, the B field off axis is given by this vector here. So our dipole moment was found to be 7.91, and the experimental magnetic field is given by this vector here with a magnitude of 1.42 times 10 to the negative 4 Teslas. The simulated field is 1.567 times 10 to the negative 4 Teslas given by this vector here with no z component. And using the percent difference formula, it was found to have a 9.57% difference between our experimental field and our simulated field. Some possible sources of this error are that there could have been other magnetic fields interfering with our measurements. There could have been inconsistent phone placement when finding the readings, and there also could have been measurement error. So what if we hadn't oriented our experiment to compensate for magnetic north, and how would this change our results? The magnetic field measurements would have been different. The X component would be different since magnetic north would contribute. The Y component would be different because the magnetic north would contribute, but the Z component won't change since the magnetic field due to Earth, or magnetic north wouldn't contribute since it's on a flat surface. At an intermediate angle, magnetic north would contribute to both the x and y components of the measured magnetic field. What if we were to stick two identical magnets together end to end and run the experiment again? How would that change our measurements, and how would all of our results differ? The magnitude of the magnetic field would likely increase due to the combination of both magnetic fields. It would likely be approximately double due to superposition, and the measured distances in the experiment would decrease due to increased magnetic field. Thank you.